Hi everyone, in this video we solve example 3.4 from the book Applied Thermodynamics, McConkey and Eastop. Here the statement of the example 4 from chapter 3. A 1 kg of steam at 100 bar and 375 centigrade expand reversibly in a perfectly thermally insulated cylinder behind a piston until the pressure is 38 bar and the steam is then dry saturated. Calculate the work done. Pressure P1 is equal to 100 bar. Convert that into Newton per meter square multiplied into the power 5 with it is now in Newton per meter square. Similarly, the temperature T1 value is 375 centigrade. The final state P2 value is 38 bar, and also it is said in the statement that the steam is expand until it is reached to dry saturated. This is, let's say, cylinder. Inside this is a piston in which expansion is taken place. This is a cylinder that is perfectly insulated, so neither heat in neither heat out is taken place. Inside this cylinder in piston there is steam that expands from superheated region and reaches to the dry saturated region. From initial state at 100 bar and pressure P1 is given 100 bar and temperature T1 that is 375 centigrade. Steam is in the superheated region. Pressure 100 bar and temperature 375 centigrade. You can see from the superheated steam table at 100 bar and temperature 375 centigrade. You can see the enthalpy value is 3017 kilojoule per kg. And also the specific volume value is 2.453 to 10 to the power minus 2 meter cube per kg. And you can also write it like this: 0.02453 meter cube per kg. Now that internal energy is equal to enthalpy minus product of pressure and specific volume. We are interested to find an internal energy at initial state point 1, what is pressure P1, that is 100 bar, multiply with 10 to the power 5 to convert into Newton per meter square. As I mentioned here, specific volume, it is 0.02453. This term we will divide with 1000 because it is in kilo, so we must convert that into kilo. So that's why we'll divide with 1000. After solving this on calculators, you will get the internal energy at state point 1, that is 2771.7 kilojoule per kg. Final state, the final state information, pressure P2 is 38 bar and the condition of the steam is dry saturated. So this final state, pressure 38 bar and steam is dry saturated. You can check the value of internal energy at the final state with the help of these pressures and dry saturated conditions from the saturated water steam table. You can see at 38 bar the internal energy value is 2602 kilojoule per kg. So the internal energy of the final state U2 will be equal to 2602 kilojoule per kg. Now from the first law of thermodynamics, work done plus heat is equal to change in internal energy. There is no heat in or out because the cylinder is perfectly insulated. Then you can say that the work done by the fluid is equal to change in internal energy. That is equal to U2 minus U1. What is the U2 value? That is 2602 minus U1 value 771.7. After solving this, you will get the work done by the fluid, that is minus 169.7 kilojoule per kg. And this is our final answer. This negative sign means that work is done by the fluid. Now let me draw its PV diagram. First, the pressure of the steam were very high. This is, let's say, initial state point 1, that is in the superheated region, and pressure of it is P1, that is 100 bar. Then cylinder piston system expand and the steam condition changes from superheated region to the saturated regions. So our final state point is in the saturated line and it follow the line. So our process will follow this line from initial state to the final state. Here the specific volume is VG and here the specific volume is V1, pressures at the final state is P2. Obviously there will be pressure drop as expansion is taken place by the fluid, and its pressure drop to 38 bar, and the steam is on the dry saturated line. Shaded area represent the work done by the fluid. This is the PV diagram of this statement. I hope you understand. If you still have confusion, you can ask in the comment section. Please subscribe my channel if you haven't subscribed, and also share with your friends and colleagues. Thank you so much.